getting used to be taped. Like this.
A bit up, so they will hear you better.
Wait. It's broke. No, it didn't. It didn't. It's fine. Thank you. All right. So I will use this opportunity to give several lectures on the subject which I call T-Tbar Deformations. Of two-dimensional quantum field theories. This is relatively recent activity. It has basically two parts. One is just regarding the subject as a part of two-dimensional theory, and there is also possible implications to telegraphically dual theories in 2 + 1 dimensions. This second aspect I will not touch at all, keeping myself in two-dimensional world all the time. I hope that that part would be addressed in other lectures here, and I hope because I want to myself learn more about it. Okay, so let me very quickly bring up the sort of what I have in mind as a plan of. So it's not that I really put this plan up to tell you that when I fail miserably in accomplishing it, you can see that I had a plan, and so that you could share my order when I will be falling further and further behind the schedule with each passing hour. All right, so there will be part 1. Well, roughly parts are lectures. So I will derive what I want factorization identity. Define T-Tbar. And describe finite size spectrum. Define T-Tbar deformation. Finite size spectrum which satisfies Burger's equation. Okay, and I will describe some properties of solutions, including 2-to-2 elastic S matrix, deformation of 2-to-2 elastic S matrix. Now, part 2 will be devoted to classical theory mostly. And will consist of T-Tbar deformations of classical actions, Lagrangians, okay, and I will here address a question of question of stability. or boundedness from below of the actions. Now part 3 will involve torus partition function. And I will derive the Cardis equation for deformed Z, the torus partition function. Then I will describe a certain technique for addressing for handling this kind of equations, general technique which I call prime forms of T of energy momentum tensor, and I will use it to derive S matrix deformation, full S matrix deformation under this T-Tbar deformation. And the part 4 consists of leftovers, including basically including generalization, extension to integrable field theories. Quantum field theories, where the presence of infinitely many integrals of motion leads to infinite family of deformations. Of which T-Tbar deformation is a particular case. All right, so this is mostly what I want to accomplish, and let me start. And I usually start this kind of talks by with strange names like this, by trying to decipher the title. Okay, so let me remove this. And try to say some words of what I mean by every symbol in this string. So there is nothing terribly mysterious in 2D. So let me start with this part, 2D. As I will be dealing in with two-dimensional space, R2, which by default will be assumed to be flat and Euclidean space. I will use coordinates. I will use the symbol X for points. X. And typically use Cartesian. So X mu will be coordinates as usual, and I will use Cartesian coordinates, either Cartesian X mu, which are x1, x2, x and y. This is already abuse of notation, because x stands for a point and for one of the coordinates, but I cannot do anything about it. There is no LaTeX on the in Blackboard writing, and so I cannot make a distinction here. All right, but I hope it will not cause any confusion here. All right, or complex coordinates. So this is going to be z and z bar equal to x plus iy, x minus iy, and as I said, it's a flat Euclidean space. So the metric is dx squared plus dy squared, or which is the same dz bar. All right, so this I think is sort of I'm sorry, a little bit pedantic deciphering of the symbol 2D. Now, a little bit more about quantum field theory. I, of course, assume that basic properties of quantum field theories are here, but I will basically use intuition coming. I will refer to intuition coming from several different viewpoints on quantum field theory, of which perhaps basic is the path integral. Okay, so that expectation value of anything is defined by the functional integral like this, x times e to the minus action of phi, where this stands for collection of fundamental fields which can be anything. By definition, my fundamental fields are integration variables in the path integral. Some integration measure is assumed to exist, and x is typically typically it's a collection of x is a collection of is a expectation. X is a product of what I will call local fields in some number, and this objects O A of x are basically some functions of phi of x and derivatives of phi and higher derivatives of phi of any order. So it's basically any composite object, local composite object built from the fundamental fields. Now the action is assumed to be, usually assumed to be a local action. So it's an integral of some Lagrangian density, which depends on phi of x and derivatives of phi of x d to x, and usually it's assumed that it doesn't involve derivatives higher than the first order. This kind of thing makes transition to operator formalism straightforward. But I mean, when you work with the renormalizations, sometimes you see that you might need to include terms of higher derivatives, and I will come back to this later in the context of renormalization group. So it might be a little bit too strict requirement to have to limit attention. So I will come back to that. So at the moment, let's assume something like this. And so this is a kind of, standard path integral point of view on the quantum field theories. But I will also, more often, this is the other source of intuition, the path integral thing. But I will also use something which I could refer as bootstrap point of view, in which we just defined field theory in terms of correlation functions. So basic objects are correlation functions. It's a collection of correlation functions. All right. And here OA, it is assumed that OA is some sort of complete set of local fields. Again, in this intuition, it's just anything built in a local way from the fundamental fields. But it is important that so it's anything built from this field, and I will use notation F for the space of so it's a space of local fields. Obviously, the local fields form a vector space because you can linearly combine them. Which is just a span. Being a little tautological, I would say it's span of this OA. All right. And what is important is that the basis in this space can be chosen in such a way that these fields form operator product expansion algebra. Okay, namely, one assumes that product of two fields can be written as a sum over these basic vectors of some in usual sense. All right. This here C are C number functions, and so it's some sort of algebra. It is understood as a infinitely many relations between these correlation functions. So one basically thinks of it as OA of x, OA1, OA2 of x prime, with additional insertions of 1 of x1 or n of xn, perhaps any kind of insertions. This can be expanded in terms of these functions CA1, A2, A of x minus x prime, and then we have OA of x prime times x, where x is a shorthand for this product. Okay, and it is assumed that this sum is a convergent. The sum over A is convergent at x1 minus x2 smaller than xi minus x2, x minus x prime. That's what I have. X minus x prime is smaller than xi minus x prime. So when the x is closest neighbor among all these other insertions in the correlation function. All right. So this is a standard notion of operator product expansion, and I mean the approach based on this is gaining more and more, becoming more and more popular when one thinks of kind of dynamical principle of quantum field theory in terms of simply as a condition of associativity of this operator product algebra defined in proper terms. Okay, so this is did I remove title already? Yes, I did. No, I didn't. So T-Tbar deformations. Well, deformations I won't even attempt to decipher. It's some sort of taking some object and representing it as a limiting case of more general class of objects, which might be either of the same class, or one needs to extend the notion of quantum field theory in this particular case, and if one needs in this particular case or not is very interesting question, largely motivating this study. I will come back to that in more details, but now in order to say what T-Tbar is, I need the notion of conserved currents in the given quantum field theory, and for that reason I will remind you the textbook kind of, you know, textbook statements that symmetries in field theory are related to conserved currents. By symmetries here I mean continuous symmetries, and conserved currents are local fields like that. They are members of this space of fields, and they satisfy the conserved means that they satisfy the continuity equation. Again, in quantum field theory, that means that the correlation functions with any kind of insertions again like this are equal to 0 if x is different from any of other insertions here, because generally when x hits one of these insertions, this is not 0, or more precisely, this is the right hand side. It consists of so-called contact terms, which are delta like terms with support at this point. Okay. So that's the meaning. Once we have this equation, I will actually, instead of that, I would, having in mind these possible contact terms, I will often write this equation in this sense, where this symbol doesn't mean that it's approximately 0 or 0.0001. It's instead a collection of contact terms. It represents possible collection of contact terms. All right. Anyways, once we have this, there is this conservation law. The conserved current leads to conserved charge. So one conserved charge or which is the same integral of motion, local integral of motion, integral of motion is basically integral of j mu of x e mu nu dx nu over some contour. I'm talking about two-dimensional space, so the integration goes along certain contour, which can be open or closed. This is a contour C, and the continuity equation basically means that you can change this contour, make a trivial deformations of this contour without changing the integral. Again, this is understood as an expression inside the correlation function, and the continuity equation tells us that any correlation function with an insertion like this doesn't depend on the precise form of the contour, as long as this contour doesn't cross any of these dangerous points where other insertions sit. What's that? This next subject. E mu nu here will be one of the heroes of this game. Is our actually our friend, unit antisymmetric object, and I will define it simply as E12 equals to +1, so it's a plus and minus antisymmetrizator. Okay, I will at certain point I will have to extend a little bit to Riemannian geometry, and then of course this can be made into a tensor by standard way. I will come back to that. All right. Anyways, after this, symmetries. I say about space-time symmetries. Here, space-time is the Euclidean version of space-time. So for Euclidean space, we have translations and rotations, and associated current J, of course, is energy momentum tensor. Which is symmetric, and again the symmetry is expressed in terms of the continuity equation for this energy momentum tensor. Well, the energy momentum tensor is derived according to standard rules from in Lagrangian field theory. Generally, it can be defined as in terms of reaction of the symmetry to small variations of background metric. If one adds one, I will also come back to that. But anyway, what is important is that we have this one, the field T mu nu, which is again which is among local fields of the theorem, and it satisfies this continuity equation, and associated charges are just momenta. P mu is integral over contour T mu nu of x e nu lambda dx lambda, and this is energy momentum, or which is the same generator of infinitesimal translations, which is to say that if I take P mu of contour C together with some objects inside correlation function, then this is equal to sum over xi belonging to inside, let's say C is a closed contour, inside C, d over dxi, d over dxi mu, of the correlation function of O1 On. All right, so you separate those x's which fall inside this contour, and differentiate, take a sum of derivatives over O. Essentially, you take all the inside of the contour, make an infinitesimal translation, and that's the action of this thing. So these are all just standard properties of field theory, written in terms of Euclidean language, or language of so this is basic setup. Now with this thing settled, I can get right to the point, defining what T-Tbar is. Okay, and that's very the basis at the heart of the whole activity is a very simple identity involving energy momentum tensor, which is so simple that I even will not need to say it can be shown or something like that, and derive this identity right in front of you. So let me remove all this nonsense. And get to something substantial. Because I really I think at this point something substantial can be said. I will use derivation, nice form of this derivation, which appeared in relatively recent work of Cardi. And it's very suggestive, so I will use it. So let me first start with defining bilocal product. I denoted T of 2 points, T of x and x prime. And this is just a combination of operator products built this way. See, this guy is important here. So then there is a T mu of x, T lambda rho of x prime. You can actually use the identity that T mu lambda E nu rho equal to delta mu nu delta lambda rho, which is of course it's in 2 dimensions with this minus delta mu mu rho delta nu lambda. Okay, and convert it into a scalar product, but I will keep this form because it's convenient for derivation. Well, the only remark is that it looks very much like a determinant in 2 dimensions. Of course, determinant of 2 by 2 matrix is something quadratic in its element, and this is the form. If this thing were the same, T of x and T, x was equal to x prime, this would be determinant of the energy moment of tensor. So it's a kind of bilocal determinant-like product. And again, in order to have a precise determinant, one needs some boring factor of 1/2 that I will not do because it's annoying to write it all the time. So anyway, the miracle of 2-dimensional continuity equation is that if I consider two-point correlation function or expectation value of this object, the local object, then one can prove that its derivative of over any coordinate is 0. So this thing is a constant, independent of x and x prime. All right, let me prove it. That's very easy, and the basis is a very simple identity. If you have any vector, let me call it k sigma, and you multiply it by e mu lambda, and then you add cycles in mu lambda nu, mu lambda sigma, then you create this way antisymmetric object with 3 indices, and because your index can only take 1 and 2 values, with 3 indices, with 3 indices available, 2 must necessarily coincide, so this thing is 0. So I want to apply this identity here using this object as k sigma over here, the derivative. So if I look at the structure, I have this e mu lambda, and so what I have here is 0, which is the right hand side of this equation, must be equal to. So let me write this cycle things explicitly. E mu lambda d over dx sigma. That's our friend here, this one, plus cycles, which are e lambda sigma d over d x mu plus e sigma mu d over dx, I think, lambda. And this acts, well, there is still remaining factor e nu rho. And then there is a mu nu effect, a 2-point correlation function, lambda rho of x primes. Okay? So this must be 0. And now let's take a look at these two terms. This one involves derivative divergence of the first entry here. And I will, in this exercise, I will assume that x is separate from x prime. And so this term returns 0. Not equal, yes. Thank you. So the second term returns 0, and so does the third term, although it's differentiation over x lambda, but because this in translationally invariant environment, I will assume translational invariance, this differentiation could be brought to the x prime, and then continuity equation for the second entry gives 0. As a result, we have only one only one term, and it must be equal to 0, which is the statement. Okay. In other words, expectation value of this x and x prime is independent of x and x prime, and several easy properties follow. So first of all, one can if we have a geometry such that infinite separations are possible, like R2, the plane which I started with, then taking limit x minus x prime to infinity, we have infinite separation here, and the 2-point correlation function then splits into expectation values of 1-point expectation values. T mu nu of x t lambda rho of x prime goes to T menu T lambda rho. These are no longer dependent. Well, I mean, the whole thing is these are no longer dependent on the coordinates. And then if I multiply here by this E mu lambda E nu rho, I find that this constant, which appears in the right-hand side here, is nothing else than this constant is nothing else than, so I find that T expectation value T of x and x prime is, well, twice determinant of the expectation values of T mu components of the energy momentum tensor. So we can compute this constant in terms of expectation values of stresses, vacuum stresses themselves. On the other hand, one could take a limit, opposite limit, x to x prime. All right. And if I ignore the possible contact terms, and at this point I define the limit as the limit of this object from the situation where they are different, I find that if I define the composite field, which I now call minus twice T-Tbar of x as some sort of limit of x prime going to x of this object T of x and x prime. Okay, then this is a composite field, and I find that its expectation value T-Tbar splits into a product of expectation values of, so it's going to be minus, perhaps, because I put minus here in my definition. So minus 2 of this is going to be equal to determinant of expectation values of T mu. Okay? What's that? No, I didn't. It's still coming.
And when you calculate when you say that you could take apart T mu,
Yeah.
where are you calculating each of the T mu at the same point?
No, here I calculate expectation values already. In translation invariant system, expectation value of a local field doesn't depend on position. So these are some constants, the constant tensor. And I take and I just made a simple observation. Then because of the decay of correlations, if I bring some 2 points apart, my 2-point function become a product of 1-point functions, which are constants, and this is the quadratic expression in terms of this constant expectation values. And what is T-Tbar and why the name comes, I will explain. I derived factorization. How do you mean factorization? Assumed. Yes, I assume the decay of correlations. In quantum field theory, this is equivalent to assuming that there is a ground state and expectation value is the vacuum matrix element. So at large separations, the vacuum contribution, if you make a intermediate state decomposition, at large separation, the vacuum contribution dominates. Is this clear? Cluster decomposition. That's another name of it. Yes. That's very standard in quantum field theory. Just like I said, it's equivalent to assuming that there is a ground state in the theory. Yes.
This first statement with T-Tbar, this is the definition of this operator?
Yes. This is the definition. So let me.
I think the last equation should not have the 2 in it.
It does. Because
That
this.
one is equal to 2 again. 2 times. Unless you get to the film now.
Wait. Yes, there is no 2 here. Thank you. All right. So I will give some exercises. Sorry. It's not really a problem to submit, but exercises. So let me give you first exercise, which is sort of trivial generalization of what I did here. Is I will define. I'll suggest you to define instead tensor valued object consider T lambda rho T nu rho of x and x prime, which is similar combination, but with one of the antisymmetrizator dropped. E mu T mu lambda of x, T nu rho of x prime. And I want you to prove that under same assumptions. Expectation value of T nu rho of x and x prime is equal to 0. No, wait a second. Symmetric combination plus T rho nu of x and x prime is equal to 0. All right. So there are many consequences from this, but in fact I will waste some time on this accomplishing the following task. I think this relation is better understood if it is promoted to operator identity. So this was identity for the expectation values. And I want to promote it to operator identity. It's more or less the same calculation. But now I work directly with the product itself, T of x and x prime. All right, and take the same derivative d over dx sigma. Again, use the same identity here, and I find then that that now, because it's no longer correlation function, the difficult part is this term, because it hits x, but the index is convoluted with the insertion at x prime. So I simply express this one as d over dx lambda dx prime lambda plus the sum of d over dx lambda minus this plus d of dx prime lambda. Okay. So this one now hits the correct entry here, so it gives 0 for any correlation function. And this one, if I write this t of x minus x prime. So let me write the object which appears here. The object which appears here. So what we have here for this term is E sigma mu, E nu rho. Then there is d over dx x lambda plus d over dx prime lambda times t mu nu of x t lambda rho of x prime. Okay, and if I use operator product expansion here for this combination, I will have a so basically what I have is let me bring these things E sigma mu here, E nu rho here. All right, and for this combination, I use the operator product expansion, which would include some C A sigma mu of x minus x prime times a collection of operators of x prime. So this combination of derivatives is designed in such a way that because the coefficient functions depend on the differences, again, this is a translationally invariant dynamics, it goes right through the coefficient function and hit only the operator. So this combination is a sum of some operators, some coefficients C A of x minus x prime, mu times A and mu times derivatives of local fields.
It's the lambda, right? The operator for lambda, not mu. C sigma lambda.
Let's see, mu is wasted. Lambda is also wasted. The index is
It's lambda.
is it lambda?
Yeah.
Yes, it's lambda, of course, because that's what eats up the lambda over here. Yes, thank you. But anyways, this is combination of terms which involve only derivatives of local fields, and I will usually write as shorthand derivative terms. For combination like this. In other words, what we have derived is that the derivative like that, if at x not equal to x prime, consists entirely of derivative terms. Okay. Now the analog of the identity which we wrote down before is to realize that this equation assumes that t of x and x prime itself is now allowed to have two kinds of terms. It is allowed to have derivative terms in it, the operator product expansion, and also the only term which are allowed beyond derivative terms are those terms whose coefficient functions are annihilated by this derivative. In other words, the only non-derivative term allowed in this combination has to have a C function coefficient equal to constant. And this operator which appears in this together with this constant term can be normalized in such a way that this coefficient is, I'm sorry, will be -2. And I will denote this operator T-Tbar of x prime, exactly as I did before. And this equation holds up to derivative terms. So this kind of term is universal. It appears in any field theory which has conserved energy momentum tensor. And but derivative terms are not really under good control. Yes.
Before that, this object has a derivative 0. That's 0.
This object, well, if I take now expectation, is it what you are asking? If I take now expectation value over translational invariant state, such as vacuum, okay, then expectation values of the derivative terms disappear, and this one becomes a expectation, the x independent expectation value of this new field T-Tbar. This is actually a very good point, because it shows that this is something which I will come back in a little later. Is that this kind of representation shows that the identity, factorization identity, which I derived, actually depends only on translational invariance and the existence of infinite separation. So the vacuum expectation value can be replaced by thermal ensemble or expectation value over any stationary state. The only thing is translation invariant. I will come back to this point in more details later. All right. Okay, so if there are no more questions, I will make several remarks, more or less notational wise. Well, one of the remarks. Let me run through few remarks. So remark 1 concerns the name T-Tbar. So this is finally discovering what the T-Tbar stands for. So if I use complex coordinates, so remark 1. If I use complex coordinates, z and z bar, which is very conventional in the conformal field theory, then it's natural to use again CFT inspired notations for the components of the energy momentum tensor. T as TZZ and T bar for TZ bar Z bar, and T and theta, I will use theta, which is not present in conformal field theory because it's 0 there, for minus TZ Z bar, and which is the same TZ bar Z. Okay. Then my determinant, like combination, become basically T of x and x prime in these coordinates becomes minus T of x, T bar of x prime, plus plus T bar of x, T of x prime, minus twice theta of x, theta of x prime, and in the conformal field theory limit, this lowest term vanishes, and the limit of x going to x prime becomes simply a product CFT, a product T and T bar, galomorphic and anti-galomorphic parts. Galomorphic and anti-galomorphic parts of the energy momentum tensor. That's why from this historical reasons, this field which is defined this way, the field T-T-bar, which in conformal field theory, T-T-bar is literally product of galomorphic and anti-galomorphic term, and the fact that it's the product for different points is independent on separation is a very trivial fact in conformal field theory. So this is the reason for the name T-T-bar. All right, so I have to speed up because I am falling dramatically behind. Now, let me quickly make this remark about the other translationally invariant situations. In particular, what I will need is now. Well, first of all, the remark is that if I have a derivative of any local field, d mu of OA of x, and take an expectation value at 0 for any for translation invariant theory, and translation invariant state. Namely, expectation value can be which is originally a matrix element between vacuum, can be replaced by any diagonal matrix element where n are any eigenstates of energy momentum. All right. Typically, the situation where it's interesting is a finite size geometry where one of the coordinates, let's say x, is compactified on the circle. So we have a geometry of a cylinder with one coordinate being a circular of some circumference r, and another coordinate being Euclidean time. Then one going from to the using the energy momentum tensor, one can define the Miltonian operator formalism, everything, and define yourself stationary states, the states which simultaneously diagonalize energy and momentum. And any of such states, of course, has a property that it's translationally invariant. So, of course, one verifies that any derivative of any local field, its diagonal matrix element in the stationary state is going to be 0. And therefore, if I use operator form of this identity, it's clear that my factorization property holds for T-Tbar n minus 2. No, T-Tbar n is going to be equal to determinant of n T mu n, the same thing. All right, this is very nice because the right-hand side can be expressed in terms of energies and momenta of the stationary states themselves. Indeed, recall that Tyy is the Euclidean version of T naught naught, the energy density. So in fact, this is minus T naught naught, right? Because y is a imaginary time, right? So this is energy density. And the result, its expectation value over any state is energy of the state, which now is a function of the size of the system, divided by R minus, because it's a Euclidean version. So I'm sorry, it's getting too crowded. This is equal to minus E n of R divided by R. Now, a Txy is I times T x naught. And so it's momentum, I times momentum density, proportional to momentum density. And so the expectation value of Txy is now I times Pn of R divided by R. And finally, Txx is the same as in Minkowski space field theory. Its expectation value is the pressure of the spatial pressure of the state. As the result, Txx is minus d over dr energy n of R. Is this clear? Okay. Then finally, this kind of expectation value, and if I compute this determinant, I find explicit expression in terms of components of the in terms of eigenvalues, and n T-Bar n is equal to minus 1 over R. And what I have here is En of R times d over dr En of R plus Pn squared of R divided by R. So it's a very explicit expression for this expectation value. All right. And finally, let me make a remark number 3. It concerns contact terms. So I say that T of x and x prime was equal to T-Bar of x prime plus derivative terms. All right. And this is valid for x not equal to x prime. So it can be violated by delta-like terms at x equal to x prime. And in some calculations, it's important to know these contact terms. And remarkably, it turns out that in 2 dimensions, the contact term, the delta-like term, which is not a derivative, is uniquely fixed by word identities. This was shown by Zohar on very general grounds from word identity related to the fact that energy momentum tensor is the current or is the response to the variation of the metric, of the background metric. And so there is a general covariance when you in play when you look at to this response. And this general covariance uniquely fixes this term. I hope to sort of at least show the Zohar's arguments more or less explicitly in one of the coming, well, maybe not coming, one of the coming probably lectures. But let me just quote the answer. And the answer is that here there is a term there is a term twice delta of x minus x prime times trace of the energy momentum tensor t mu mu of x prime plus this one. So let me write the full expression plus T-Tbar of x prime plus derivative terms. So now this is a full identity written up to derivative terms. Yes.
What would happen if I would try to do the same exercise with JJ bar? If I do a Sugawara construction, and I will decide I want to add this term.
Okay, so if you have only one component of the current, then you get 0. You get something which you could figure out on so your JJ bar expectation value. So no, it's not JJ bar. It's basically identically 0. You need to antisymmetrize. So if you have two currents, J mu 1 mu and J2 mu, you need to add E mu here in order for the whole machinery to work. If this is the same current, when you bring them together, you expect 0, and you get 0. Okay. Now, if you have two different currents, then you get interesting things. And we are playing actually with the situation where you have just two currents, two conserved quantities, two components of the energy momentum, and we are playing this game. Now, if you just take here the currents which are responses to which are related to some U1 phase symmetries of the theory, and form this combination, you get the model which is known for ages, Federer-Busch model, and it admits some sort of exact solution, but it's sort of trivial because the deformation of the scattering matrix is just adding a constant phase, and for that reason, I think it was considered not particularly interesting situation. It's unexpectedly in some ways. It turns out that if you consider not U1 but some space-time symmetries, it produces something more contentive. That's is that the answer? Addresses your question? All right. I might comment on Federer-Busch model and more general things again in one of the future lectures which are in danger now. All right. So this is now the full form, including contact terms. So it's valid as distribution. So you now can integrate this identity over X with this term. Now before turning to what I call T-Tbar flow or T-Tbar deformations, let me say some words about sort of just a quantum field theory, and this object which we define this way has interesting implications to critical behavior, to critical singularities. Namely, it gives some predictions about subleading term in singular expansion around critical point. Let me remind a little bit. Suppose I have some statistical system and control parameter which I denote mu, so that criticality occurs at mu equal to 0. Mu can be like temperature, T minus Tc, something like this, or some other critical parameter in the theory. So mu is a deviation from the critical point. All right, so when mu approaches to 0, the various thermodynamic quantities exhibit singular behavior. So, for instance, specific free energy behaves like, let me call it F naught plus F singular, where f naught is some regular function, absolutely analytic at mu equals 0, while f singular behaves like some coefficient, some amplitude a times mu to certain general fractional power plus subleading term. So this usually is no. Okay. So let me postpone.
This is the heat capacity exponent, not mu. It should be alpha.
Yeah,
It's called alpha usually, the heat capacity exponent.
no, it's heat capacity. It's related to heat capacity, but it's also related to nu by scaling relation.
Yeah, yeah.
And I already solved this equation in 2 dimensions. That's in 2 dimensions. So this is nu is a correlation length exponent. So let me. So correlation length RC, which I denote as m minus 1, the gap. So the gap behaves like some coefficient b times mu to the nu. That's the definition of correlation length exponent. Okay, so RC diverges as mu to the minus nu, and these terms are just the first terms in some singular expansion. So what will follow here is a prime times mu to some other power x greater than 2 nu plus other terms, and b prime is going to be mu to the y correction term. So this comes as first terms of long infinite singular expansion. And while these first term leading terms are under control of the true honest quantum field theory, in particular this amplitude and everything are completely universal as long as we are sitting in the same universality class controlled by the same fixed point. I will say a little bit more words about it, but this the subleading terms are less universal, and well, basically the nature of these subleading terms can be understood in terms of renormalization group. So basically, just like I said, this kind of given universality class is determined by certain fixed point. So we have some fixed point, I call it A star, a fixed point. So that this is fixed point, and the renormalization group flow in the vicinity involves some relevant directions which flow away from this point, and then there are some irrelevant deformations. So if I have some canonical surface here, or spanned by microscopic interactions like I don't know, lattice interactions or whatever, the collection of molecules with short-term short-range interactions, and so forth, then renormalization group brings us from this surface to some may bring us to some vicinity of this fixed point, and the critical value mu equals 0 is exactly the critical point is where you flow down to the fixed point. So if you are close to it, you go like this. But in any event, you are dealing with when you are dealing with the fixed point, you could look at the expansion in the vicinity of this fixed point, which looks like this. The action in the vicinity of A star, it's A star plus mu times the relevant operator. The relevant operator is phi delta is the direction along the unstable manifold,
And there are many operators which may appear here. So this is relevant. So the dimension d, which is 2 delta, is greater is below 2, and these are irrelevant operators. So their dimensions are greater than 2. I will ignore the possibility of marginal operators because it's not really important for this analysis. But anyway, if one looks at this part, so looks at this part is honest quantum field theory, which determines the leading singularities and critical behavior. Now the subleading terms of this kind come from this irrelevant parts. Irrelevant parts are basically the operators along which it flows down to the fixed point, and so from this one can derive that while nu relates to the dimension of the relevant operator, it's 2 minus 2 delta to the minus 1. Then the dominating subleading singularity relates to the least irrelevant among the irrelevant operators. So if I arrange these dimensions di in the growing order, d1 smaller than d2 and all the rest, then d1 is the dominating irrelevant operator, and it's easy to see that x is related to this dimension. It's d1 times nu, and y, it's just simple dimensional analysis, d1 minus 1 times nu. This is just a simple dimensional analysis, but something more predictive comes if this one, as it often happens, the least irrelevant in some cases. Actually, in many interesting cases, as I say, the least irrelevant is this T-Tbar. I don't know if you paid attention or not, but the calculation, the factorization property, assumes that dimension of T-Tbar is exactly 4. Okay, so it's a relevant operator, and in many cases, examples are like Young-Lee singularity, or even the Ising model transition, universality class. The least irrelevant operator is T-Tbar. Okay, in that case, this identity which I derived allows one to make some prediction about the amplitudes A prime and B prime.
So it's true that the spectrum of irrelevant operators is discrete?
I use the intuition, which I assume that the whole spectrum of the dimension is discrete, or at least I need at least some lower operators to be discrete in order to make. If not, I mean, this kind of singular expansion would take a lot more complicated form.
Beforehand you said that you don't care about the marginal operators. I guess this is not true anymore. One is the least irrelevant one.
Well, if you have marginal operators, then you have to distinguish irrelevantly marginal from relevantly marginal, but basically the rest of it goes the same.
Yeah.
Well, but if you have a marginal operator, let's say irrelevantly marginal operator, then of course this kind of singular expansion, again, you will have logarithmic terms and all this stuff which you have, for instance, in near criticality in d close to 4, or d equals 4. All right, this logarithmic corrections. I don't want this complication to come in, so I assume that, yes, I know. So anyways, I just say flatly, I will derive this, what I'm going to state, I will derive a little bit later in probably in next lecture in a little bit more general context. But it turns out that from this identity it follows that b prime over a prime equals to b over a, the relation for amplitudes, which is the only reason for it is this factorization identity. In that case, d1 is just like I say, d1 is 4. So you could compute that x is 4 nu, and this is 3 nu, and then the relations, the amplitude obey this relation. In fact, I mean it seems to be kind of fancy, but precision calculation of the singular expansion, for instance, in Young-Lee singularity, shows this with great precision. All right, so let me now, I know that there are less than 5 minutes, but let me still start the main subject here. I actually want to take this expression, which I just carelessly erased. I want to take this expression a little bit. So the next will be T-Tbar, what I call T-Tbar flow, defining T-Tbar flow.
Is T-Tbar a Virasoro descendant?
In conformal field theory, it's Virasoro descendant. Away from conformal field theory, there is no Virasoro algebra.
Let's say in 2D Ising, it's a Virasoro descendant.
In 2D Ising, at critical point, it is a Virasoro descendant. So I can write my action as a star, fixed point, and in 2 dimensions this is going to be conformal field theory. Plus, let's say I have a relevant operator here, and then I don't know. No one warned me that it's not legitimate thing to do. I add all these irrelevant operators here, sum over I. And of course, I mean, if I look at the textbook, I'd say that it's not a good idea to take this kind of expression seriously, and there are many reasons for that. First of all, it's if one tries to arrange a perturbation theory in this kind of parameters alpha, it leads to non-renormalizable perturbation theory with all this kind of, problems with accumulating divergences at higher orders, necessity to bring in higher and higher dimensional counterterms. And so one can, in principle, if you have this space of fields F, which consists of all these local operators, you have enough material to furnish all the counterterms, but then after cancellation of the divergences, you have a remaining finite parts which make kind of this kind of expression. We say that it doesn't define a theory because you need to together with the theory you need to define a subtraction scheme, and now the physical content of the theory, unlike renormalizable perturbation theory, physical content of the theory now depend on the subtraction scheme. And people say, I mean, textbooks say that the theory loses predictive power. Because basically writing down Lagrangian or action or something doesn't define the theory, which is true. But I think much better way of understanding it is in terms of Wilson's renormalization group. I will generally assume that basic idea of Wilson's renormalization group 0. Okay, Wilson's renormalization group. I think I have a temptation to drop this part, but I think it's very instructive and largely explain motivation behind all these things. So I will next time, maybe at the price of some items in the plan, I will describe this. All right. Okay.